All right, before we start number 3, I want to go back and look at, let's see, this guy. Okay, so this is kind of the steps we're going to use for optimization. And now that we've kind of done 2 problems and kind of got the general feel of what's happening, I thought it would be good to read it again. So we'll start by drawing a picture, and then we're going to read the problem to see what it is we're trying to minimize or maximize. Then we're going to write an equation that models that situation. And then for number 4, we're going to find the input value that maximizes or minimizes our objective equation. Now, to do that can be tricky sometimes. We just saw that sometimes that function that models our situation, it has multiple variables. When that happens, we have to find a constraint equation, something that limits it or keeps it from expanding forever or minimizing forever. That's called the constraint equation. Then we use the constraint equation to rewrite the objective function in one variable. Then we find the optimum values for x and y. So let's give that a shot. On number 3. Oh, stuck. Okay. A 1,000 square foot lot is to be enclosed on 3 sides by fencing that costs $10 per foot, and on the 4th side by shrubs that cost $15 per foot. Okay, now that I've read it, this is a problem I see on tests a lot. So I've got a lot that has fencing on 3 sides, sorry, English is hard. And then there's shrubs on the 4th side. So it's a rectangle because it says 3 sides, 1 side, and it's a lot. So we're gonna say if this here is length L, then this side is L, and this side would also be width. These two are widths. And I was told that the fencing costs $10 a foot. And the shrubs cost $15 per foot. Okay, I also know that it's 1,000 square feet. So the whole thing, the area is 1,000 square feet. So that's a lot of information. Find the dimensions of the lot so that the cost of fencing and shrubs is minimized. So objective, minimize cost. Oops. Objective, minimize cost. So I need a function that gives me the cost. So to figure out the cost, let's see, that would be 10 feet times L. So I'm trying to figure out what the cost would be. I'm not going to worry about minimum or max. I'm just going to find an equation. And I know that this one side here, it's $10 a foot, and there are L feet, so that would be 10L. And then this side here, it's also fencing, so that would be 10W. This side is also fencing, 10L. And then the last side is shrubs, that's $15, and it's W feet. So I can simplify that a bit to 20L plus 25W. Now this is that problem again where I've got 2 variables here, an L and a W. So I need something that would make it so that I can't just do 1,000,000 feet of fencing, something that holds it back. And I actually think that would be that area is equal to 1,000 square feet. So I know that the area has to equal 1,000 square feet. And area would be the width times the length. So W, L, we'll go like that so you can tell it's an L and not a 1. So I'm going to take this constraint equation and use it to simplify or rewrite my cost equation into one variable. So I think I'll just divide by L. W equals 1,000 divided by L, which I'll then plug into my cost equation. So this is kind of like a brief side note. So I'm rewriting my cost function to be 20L plus 25 times 1,000 over L. So now I have it in one variable, and the variable is L, so I actually shouldn't have X there, it should be an L there. That's the thing that I want to find the minimum for. So to find the minimum, I will find the critical points by taking the derivative. So C prime of L. So 20L, L is what the derivative were like, it's with respect to L, so that would just be 20. And then this one is a little hard to take the derivative of, so I'm going to rewrite the original equation so that the L is in the numerator. So 20L plus, let's see, 25,000 L to the negative 1 power. Since it's written like that, it's a little bit easier to take the derivative. The derivative would be 20 minus 25,000 L to the negative 2 power, or 20 minus 25,000 over L squared. So this is my derivative. To find the critical points, I look to see where I can't take a derivative, and one place is L equals 0, right? I can't divide by 0. So L equals 0 is one critical point. But maybe there's more. And the reason why I hope there's more is the interpretation of L is that the length of this fence here is 0. And if I'm trying to find the minimum cost, that would definitely work. It would give me a minimum cost, but it would also make it so that there's no area at all. So that's not going to work. So I'm pretty sure that that one's out. I'm not even going to bother with that one. But I will set the derivative equal to 0 and hope there's another one. So I am going to move 25,000 over L squared to the right. And then I'll multiply by L squared. So I get 20 L squared equals 25,000. Oh, my stomach just rumbled. I'm sorry. Divide by 20. And that gives me L squared equals 25,000 over 20. Let's see, what is half of 2,500? I think that's 1,250. Let me double check my mental math there. Yeah, okay. So I get 1,250, and then I need the square root. 1,250, which I'll do in a calculator. That is roughly 35.4. Okay, so this is a critical point that's a little bit more reasonable, but I do want to check to make sure that that is actually a minimum, because what if I was actually maximizing? That would be bad. You know, I don't want to maximize cost, I want the minimum cost possible. So I will take the second derivative just to be sure. I'll do that over here. Second derivative. Derivative of 20 is 0. And I'm taking this derivative minus, actually that would be 50,000. And then L to the negative 3rd power. And then, so if I plug in my critical point, or really close to it, 35.4, that's 50,000, and then times 1 over 35.4 cubed. So that's definitely something positive. So that's a good thing because that means it's concave up when x is 35.4, or I guess L, when L is 35.4. So that's definitely a minimum. So to write that out, we have a minimum at L equals the root of 1,250, and I think that's in feet. And I bet there's more to this question that we need to answer. Find the dimensions of the lot so that the cost of the fencing and shrubs is minimized. Okay, so I need the dimensions, which means I also need W. And what do we know about W? Oh, W is 1,000 divided by L. W equals 1,000 divided by L. Cool. So now I have my length and my width. Okay, if you have any questions, ask them on the discussion board.